Okay, so let us start. So we are still talking about chapter 11. Okay, so we are still talking about series, the theory of series. So last time I already explained. So essentially what we are talking about is such an object. Now, last time I already explained to you what is the meaning of this object. What we actually do is we look at the partial sums. So we sum the first n terms. And look at this sequence. And if this sequence is convergent, so if this sequence converges to an S as n tends to infinity, then we will say that this kind of object here exists, or the series is convergent, and we will say it has the value S, which is in the limit of the partial sum. So this is the meaning here of this object here. And if this sequence does not converge, then we will say that this series is divergent. So last time we already looked at some very easy examples. So you know the standard example is this one. This is the example you know already from high school. So you know that if the absolute value of r is smaller than 1, then this series will be convergent, and this will be the sum. And if the absolute value of r is larger or equal than 1, then this series here will be divergent. Okay, so maybe let's look at one example which is related to this, which is maybe a more interesting example. So let's look at the closed interval from 0 to 1. Okay, so what we are looking at is this closed interval here. Now, what we do in the first step is we remove so we actually divide this interval into 3 subintervals of equal lengths, and we remove the middle. Okay, so if you divide this into 3 subintervals, then you have here, okay, so this is 1 over 3, this is 2 over 3, here 1. And what we do is, okay, we remove the middle. Okay, so you remove this here. Okay, so after the first step, we are left. So actually what we remove is the open interval from 1 over 3 to 2 over 3. So what we are left after the first step is, okay, we have just this part here, from 0 to 1 over 3, and from 2 over 3 to 1. So this corresponds here to the union of 2 intervals. So this interval, and then joint with with the interval from 1 over 3 to 1. So we just have the union of those 2 intervals. Okay. And now what we do is, okay, so essentially the set looks like, if I use orange to denote the set now, so the set looks like this here and this here. And now what we do is, okay, we look at both of them and remove again the middle. Okay, so we again divide this interval here into 3 pieces, this interval into 3 pieces, and we remove the middle. And we go on like this. Okay. So after we have proceeded 3 steps, we are left with the following. Okay, so we have here 0, we have here 1 over 3, we have here 2 over 3, and we have here 1. And actually we have just removed the middle. So what we have here is just this here, and this here. And here we have this, and this here. Okay, and then we go on like this. Okay. So what we get here is, of course, you see the yellow set here. What is left is getting smaller and smaller. Okay, so we go on like this until infinity, and the resulting set of the points which are left over after you continue this process. So now you will remove this and this and this and this, and you go on like this. It's called it's normally denoted by C. Okay, so this is called the Cantor set. Okay, so how is this related to this series here? So what I want to compute is, okay, what is the length of all the intervals which I have removed? Okay, so here in the first part, here I remove an interval of length 1 over 3. Here in the second step, I remove 2 intervals, both of length 1 over 9. And then if I go on like this, in the third step, I will remove 4 intervals, all of them of length 1 over 27, and I will go on like this. Okay, this is essentially what I take out from this set. So let's look at okay. So what I ask is, what is the length, the overall length of all intervals removed. Okay, so this is not complicated to compute because here you see the length of the interval I remove in the first step 1 over 3. The length of the interval removed in the second step is 2 over 9, and then the length of the interval removed in the of the sums of the intervals of the lengths of the intervals removed in the third step is 4 over 27, and so on and so forth. So what I have to compute here is okay, so maybe I delete this. Okay, so the answer here of this overall length is okay. So in the first step, I have 1 over 3 for this interval here. The second step, I have 2 over 3 square because I have 2 intervals of length 1 over 3 square, and then I go on like this. So in the third step, I have 2 square over 3 to the 3 plus and so on. And you see, okay, what I get here is exactly the same series, okay, which I have considered before. So you see that, okay, if you use our formula, then this is 1 over 3 times 1 over 1 minus 2 over 3. Okay, so you see the answer is 1. Okay, this is somehow quite interesting because this means, okay, what you remove, if you look at the length of the intervals which you remove and you add all of them, is equal to the length of the original interval. But if you continue this process an infinite number of times, in the Cantor set there will be still many points left because like 1 over 3 you will never remove this point, and also all other these 2 endpoints of this interval you will never remove. So also the Cantor set, the set C, is pretty huge because there are certainly an infinite number of points in it. You see that if I do this, what I remove, okay, is equal to the length of the original interval. So this is a famous example in mathematics. This Cantor set is a simple example for what we call in mathematics fractal. This is one of the exercises you find in our textbook. You might have heard of such objects, fractals, which are used to, for instance, to generate computer simulations of the structure of coastlines and so on. So they have many applications. Maybe you have heard about this. In Chinese, they're called soixin. Okay, so now this was one example here for where the geometric series naturally arises. Now, last time we also looked at other examples of convergent and divergent series. We saw another important example was this one. Okay, so this the so-called harmonic series. Okay, so in order to understand whether this series is convergent or not, what we have to do is we have to look at the sum of the first n terms. Okay, and we have to discuss the behavior of this sequence here. So last time I showed you that this sequence tends to infinity as n tends to infinity. Actually, I showed this for a subsequence of this sequence. But since the sequence is getting larger and larger, because what you do is you add positive terms, if you know for a subsequence because last time I showed that this here tends to infinity as n tends to infinity. You remember? I grouped the terms suitable, and then I could show, okay, this is getting larger and larger. But if I know that this here tends to infinity as n tends to infinity, it's clear that Sn has to go to infinity as well, because here, because all the terms here are positive, and Sn is increasing sequence. Okay, so this series here is divergent, and this is actually an important example for a divergent series. Normally here in mathematics you find very often that the sum of the first n terms is denoted by Hn, and Hn is what we call in mathematics harmonic numbers. Okay, as n gets larger and larger, harmonic numbers will get larger and larger. Okay, and we also saw some other examples of series where we could easily determine whether the series is convergent or not. Okay, so one of our main aim in the next maybe three chapters or three sections is to figure out, okay, you've given a series. What we want to know is whether the series. Of course, the first question is always whether the series is convergent or not. Now, so far we do not have any results, okay, which tell us how we can easily determine whether a given series is convergent or not. Because obviously, always looking at the partial sums would be very complicated. In this case, we were able to discuss the behavior of the sequence of partial sums, and also for the geometric series, it was easy because we could compute Sn, and for some other examples you have seen last time. But if you look, for instance, at this series, if you look at this series here now, if you are asked to discuss whether this series is convergent or not, okay, so the only method we have at the moment is we look at the definition. Now the definition tells us, okay, look at the sequence of partial sums, okay, and determine whether this sequence is convergent or not. Now, okay, unless we know some trick, but for this it's not so easy. Okay, it's not so easy to determine whether this sequence is convergent or not. The real problem is coming from the fact that you have a sum here, you sum up terms. This makes it more complicated. If you can find for this sum some expression, if you can sum this somehow, then of course you can just discuss the expression, and then it will be much easier. But we see that even for this easy-looking series, it doesn't seem to be straightforward to figure out whether the series is convergent or not. And what we want to do essentially in the next three sections is to learn a couple of tests which help us quickly to determine whether such a given series is convergent or not. Okay. For instance, for this series, you could use a calculator. You could compute Sn for n larger and larger, and you will find out it seems to converge to a number. Okay. Today we will essentially learn tools how to prove that or how to determine that this series is indeed convergent. But this is the first problem actually you have for a series, figuring out whether the series is convergent or not. Once you know that this series is convergent, of course, the natural second problem is, okay, what is the value? And as I already emphasized last time, finding the value is much more complicated than figuring out whether a series is convergent or not. We will see this for this example here. It's a good example because today we will already understand why this series is convergent, but it will take us 4 months in order to have tools to compute actually the sum, the limit. So it's not so. This is here computing the sum. Once you know that the series is convergent, is not such an easy problem. Okay. Now, the first thing we observe for a convergent series is the following result, which is already useful in order to determine whether a given series is convergent or not. This is also the first result you see in our textbook. Okay, so if you have given a series which is convergent, then if you look at this sequence here, this sequence must tend to 0 as n tends to infinity. This is something actually you expect, because roughly speaking, this series is convergent means, okay, you can sum up all those terms, okay. Now, if an is not getting smaller and smaller, okay, if you start summing up the terms, okay, the partial sum will get larger and larger, okay. So this is something you certainly need, which certainly has to be satisfied if a series is convergent. Of course, the proof here is trivial, because what we do is we look at the partial sums. Okay. Now, so by assumption, you see the assumption is that this series is convergent. So the assumption is that this Sn tends to some S as n tends to infinity. This is the definition of convergence. And now, if you look at okay, so if you look at An, so you easily observe that you can write An as Sn minus 1. Okay, so if n tends to infinity, then you see that this sequence here tends to S, and this sequence tends to S as well. So what you get is 0. Okay, so actually the reason is trivial, why, or almost trivial, why for a convergent series, An must go to 0. And this actually gives you already the first test, okay, for in order to determine whether a series is divergent. Namely, you know, whenever this fails here, okay, whenever An does not tend to 0, okay, you can immediately conclude that the given series is divergent. Okay, and this is called in our textbook the divergence test. So whenever you have given a series, okay, the first thing you should try to check, the first thing you should check is whether the terms tend to 0, because otherwise you have to do nothing, because the series will be automatically divergent. For instance, here's a very easy example. Okay, so for instance, if you have given this series here and someone asks you, okay, whether the series is convergent or not, you can immediately conclude that this series is divergent. Because if you look at the sequence of terms, which is k squared over k squared minus 1, and you let k tend to infinity, then this here goes to 1 as k tends to infinity. And 1 is not equal to 0. Okay, so from this, you know already that this series is divergent. You have to do nothing. Now, of course, it would be very, very convenient if also the inverse would be true. Namely, if whenever you have given a series and you see that An tends to 0 as n tends to infinity, okay, that they could conclude that the series is convergent. This would be very convenient. But we know already one example, okay, of a divergent series where An still tends to 0, okay. So the inverse does not hold. So you just have to look at this example here. The harmonic series, okay, is divergent. And 1 over n tends to 0 as n tends to infinity. Okay. So it is true that the convergence of a series implies that An tends to 0 as n tends to infinity, but the inverse is not necessarily true. If the inverse would be true as well, okay, the theory of series would be trivial, okay, because then you just check this one, and you can immediately, for every series, conclude whether a series is convergent or not. Unfortunately, it's not so easy. Okay, you have something like this here, and this somehow tells you, okay, the reason why this series is divergent, okay, we will just understand them better and better, is, okay, the terms tend to 0, okay, but they do not tend to 0 quick enough, okay. Now, if you replace here 1 over n by 1 over n squared, okay, 1 over n squared tends to 0 much faster than 1 over n, okay, and for 1 over n squared, we will indeed see that the resulting series or the corresponding series is convergent. Okay, so here essentially the reason why here the divergence fails is because this sequence does not tends to 0 as n tends to infinity, but not fast enough. Okay, so any questions to this? So always keep in mind the first thing you have to check if you have given a series and you have to figure out whether the series is convergent or not. Always the first thing, check whether the terms tend to 0. Okay, because if they do not tend to 0, you do not have to use any other tests. We will learn in the next 3 sections quite a lot of different tests. Okay, which help us then to understand which you can apply in order to check whether a series is convergent or not. Okay. But the first thing you always should check is this condition here. Now, whenever a series is convergent, you have all the properties you would expect from a sum to hold also for a series. So whenever you have, this is another theorem in our textbook. Okay, so if you have 2 series which are convergent, then if you look at this series here where the new terms are an plus bn or an minus bn, then this is equal to the series over the an plus or minus, and then the series over the bn. So this is something you would expect from a sum to hold. It's also true for a series. And if you have a series c times an, then what you can actually do is you can take out the c. Also, this is what you expect from a sum to hold. Okay, so all those properties actually are expected because you have those properties for sums. Okay, but they hold for series as well. But you have to be a little bit cautious here because we will later on see some of the properties you are used from the sum are not true for a convergent series. Okay, so those properties are true. Okay, and you should. This is something I already stressed last semester several times when talking about the limit laws. Okay, so you should. It's important to notice that we assume that both series are convergent. Okay, so this assumption here is important. Okay, if this assumption is not satisfied, okay, you are not allowed to. If you have to consider the series of the sum, you are not allowed to break it into 2 parts. Okay, it's not necessarily satisfied. Okay, so an easy example is if you look at the first property and you have an is equal to, let's say an is equal to bn is equal to 1 over n, and you look at the minus property, okay, then you see that this series here, okay, is convergent, but you are not allowed to break it into 2 parts. Because those two guys are both divergent. Okay, so this relation here just holds under the assumption that those 2 series are convergent, and you should read it like, okay, if this series is convergent and this series is convergent, then this series is convergent as well, and you can compute, and the sum of this series is given by the sum of the values of those 2 series. You should read it like this. So this is important to notice. So the assumptions are important. Okay, we saw this already. This is essentially the same remark as for limit laws. We saw for limit laws also the assumptions are important. You see, for instance, but you have some results if you have kind of results in case you assume, for instance, that this series is convergent and this series is divergent. Okay, if this series is convergent and this series is divergent, then the sum will be divergent. Okay, the reason being simple because you assume that the sum is convergent. Okay, but then you know that this series is convergent as well, and then you use this property by subtracting and you would get that this series is convergent as well. Okay, you understand this kind of reasoning? So if this series is convergent and this series is divergent, then this new series divergent as well. I just told you the proof by contradiction. Okay, now so these are some simple properties, and maybe I want to stress once more that okay, this is something you would expect from the rules which are true for sums if you replace the series by sums. Now later on we will see that not all rules which are true for finite sums are true for series as well. Okay, we will identify later on some of the properties for finite sums which do not longer hold for a series. Okay, now the next thing, as I have already stressed, is we want to essentially we want to have some good tests which help us to, for a given series, to test whether the series is convergent or not. One trivial remark is if you have given a series, you can throw away a finite number of terms. Okay, this will not affect whether a series is convergent or not. Okay, so if it is, sometimes it's more convenient to, you have given a series, sometimes it's more convenient to throw away, for instance, the first 10 terms. We will see examples why this is sometimes convenient, but it's trivial that if you throw away a finite number of terms, then and you know that the series where you have removed the finite number of terms is convergent, then this series will be, the original series will be convergent as well. It's trivial remark. Now, the first test we are going to discuss is the so-called integral test. Now, this is already for this series here. Okay, so we want to figure out, okay, is this series convergent or not? Of course, as I already said, you could use your calculator, and you could look at the partial sums. You could first maybe you can spend a little bit time thinking about whether it's possible to find an expression for this, but it's not so easy. You will figure out. So the only thing you can do is, okay, you plug in some values for n and compute Sn and make n larger and larger, and you will indeed see, okay, this seems to converge. So from computation, okay, it seems to the Sn seems to approach some limit as n is getting larger and larger. Now, how to prove this? So how to prove that? So this then suggests that this series is indeed convergent. But how to prove this result using a more precise way to do it, not just doing numerical computations. Now, an easy way is you look at the following picture. So actually, we look at this partial sum here. So we have here 1 and 2 and so on, n minus 1, n. Now what we plot is this function here, so f of x is equal to 1 over x squared. So this function looks like, okay, so something like this here. Now you see, okay, so how can you interpret this sum here? So this sum, if I plot the following rectangles, okay, this is the last one. Okay, so if I plot these rectangles here, then you see that if you compute the area of these rectangles. Okay, so the area of these rectangles is exactly the Sn here. Okay, so the Sn, which is the area of these rectangles. Okay, but here you see that you can bound this sequence from above by, okay, you choose the area of the first you take the area of the first rectangle out, which is 1 plus. And for the rest, so the rest is, just from this picture you see, is smaller or equal than the integral from 1 to n, and then dx over x squared. Okay. Now, this is again smaller or equal than 1 plus. Now, because this function is always positive, so you can extend the integration to infinity. Okay, but this you can easily compute is equal to 1, so what you have is 2. Okay, so you see that the Sn is smaller or equal than 2 for all n. Okay, this is not enough to conclude that as n tends to infinity, Sn converges, but we have if you look at the sequence Sn, because all the terms here are positive, so you add always something positive. So Sn is certainly increasing. So you see that Sn is increasing. You see that Sn is bounded from above. So you can conclude Sn is convergent by the monotonic sequence theorem. Okay, so Sn is increasing and bounded from above. Okay, so we can use our, I call this monotonic sequence theorem, okay, MST. We can use our monotonic sequence theorem and conclude that Sn is convergent. So the limit as n tends to infinity of Sn exists, and this is equal to some s. And this then means, by definition, that this series here is divergent, is convergent. Sorry. Okay, so this is essentially the way we are going to reason, and you will see this kind of you will see this way of reasoning again and again now in the next two or three sections. So you see that you have an advantage if you have a series whose terms are all positive, okay? Because for such a series, if the terms are all positive, okay, if you look at the sequence of partial sums, this sequence is an increasing sequence, okay? So in order to prove that a series of positive terms is convergent, you have just to show that this sequence is bounded, and that's it. Okay, so this is the important idea, and this will be essentially the reason why if you have a series where the terms are all positive, are much easier to handle than the case where the series where the terms also might be negative, positive, negative. Okay, so essentially this will be our main idea in order to show that, in particular in this section, in order to show that the given series is convergent. Now, how about divergence? So let's look at another series. Okay, so for instance, let's look at this series. Somehow similar, okay? But the only difference is now that the exponent of n is not 2, but 1/2. Now, for this series, okay, if you again start by doing some computations, so we look at the partial sums. Okay. If you again start by doing some computations, so you choose some values for n, you plug in and you sum this up, and you make n larger and larger, you will see that okay, this seems to tend to infinity as n tends to infinity. Okay, so your guess is that this series here is divergent. Okay, now how to show this precisely? So here again we use a similar picture, but it's slightly different to the picture before. So we have here x, we have here y. We look now at we look again at the function f of x is equal to 1 over the square root of x. Okay, so we have here 1, we have here 2, and we go on like this. Then we have here n, and here we have n plus 1. Okay, now what we are looking at again is this function here. Okay, so this function. Now you see that before we look. So essentially, we have to look at these heights here. Now, before we have drawn the rectangles such that we we draw here a horizontal line in this direction. Now we just go in the other direction. Okay, but it's essentially the same idea. So now we look at it like this here. Okay, so here we have the next one, and here we have the last one. Okay. Now what you see here again, if you look at the sum here of these areas. Okay, if you look at the sum of these areas, the sum of these areas will again be equal to Sn. Okay, so Sn. Okay, but the advantage is now, if you look at things like this here, the advantage is now from the integral you get a lower bound. You see that this is larger or equal than the integral from 1 to n plus 1. So you integrate from here to here, and the area below the yellow function, so dx. Okay. Now we remember that last semester, okay, we looked at this integral here. Okay, and we showed that this integral here is convergent if p is larger than 1, divergent if p is smaller or equal than 1. Okay, and because here the area, because here you can interpret this as the area below this function, the area must, of course the area is positive, okay, because you have a positive function here, the area below the function above the x-axis. So you see, in this case, okay, the integral, because you add more and more, so divergent in this case means that as n tends to infinity, this here has to tend to infinity. Okay, so we know already from last semester that this tends to infinity if n tends to infinity. So the lower bound tends to infinity as n tends to infinity. So Sn goes to infinity as n tends to infinity. And this shows that by definition that this series is divergent. So our guess was correct. Okay, so you see this idea is very useful. Okay, of if you have given a series, okay, you see essentially what you have to do. So you have given the series here. You have to define a function such that the function, if you plug in positive integers n, what you get are the terms here. Okay, then what you need for this assumption that this picture here always works is so this function must be continuous, of course, because otherwise you cannot look at the integral, but also decreasing. Okay, so continuous and decreasing. Then, if you have such a function, okay, which at the positive integers is equal to your terms, and the function is decreasing and continuous, from this kind of general reasoning, you see that you can replace the series, okay, by integral. So by the integral from 1 to infinity of f of x dx, and the series will be convergent if and only if the integral will be convergent. We saw one example for the that convergence of the integral implies convergence of the series, and this is an example that divergence of the integral implies divergence of the series, and this you can easily turn into a general proof. So this test, which I just mentioned, is called the integral test. Okay, so this is the integral test. So assume that you have a function f of x which is positive, decreasing, and continuous. And you have a sequence which you obtain by evaluating the function at positive integers, then this series is convergent if and only if this integral here is convergent. Okay, so this is the first test which we are going to use. Now, for this test, you see that what you need is that an is positive. So we look always at series where all the terms are positive. This is the first thing. And the second thing is what you need is you need to find such a function which is decreasing and continuous. Now, essentially, it is enough if this function is decreasing from some point on. Okay, this is enough. Not necessarily from this point 1 on. So it's enough if this f of x starts to decrease for some large x. Okay, because as I said, you can throw away a finite number of terms. This will not affect the convergence behavior of this series. Okay, so if the function you find starts to decrease for some large x, okay, you just throw away the first few terms which cause problems, and you apply this result here. Okay, so essentially what you have to check is not that the function is decreasing for all x larger or equal than 1, as you see in our textbook. In the original formulation of the theorem, it's enough to figure out that the function starts to decrease from some point on. Okay, so let's look maybe at some examples. Now, this already gives a very important class of series is this one. Okay, so we discussed already two cases, namely three cases. P is equal to 2, we know already convergent. For P is equal to 1, this series becomes the harmonic series, so we know divergent. And for P is equal to 1/2, we also saw divergent by using this here. Now, actually, because I just told you that the integral, if you look at this integral from 1 to infinity, dx over x to the p, this integral is convergent if and only if p is larger than 1. Okay, the only thing you have to notice is this test you can just apply if p is larger than 0. Okay, for p is smaller or equal than 0, you cannot apply this test here. So if p is smaller or equal than 0, okay, you have to do something different, but p is smaller or equal than 0 is easy, because in this case, these terms do not tend to 0 as n tends to infinity. Okay, so you can use the most simplest test in order to derive that if p is smaller or equal than 0, this series will be divergent. And for the remaining cases, you can apply this test here. So maybe for one example, I do this more precisely. Okay, so p is smaller or equal than 0. Okay, so here we look at the series. We always look at the series here, so I don't have to write this. So if p is smaller or equal than 0, then the limit n tends to infinity, 1 over n to the p is not equal to 0. Okay, so from this immediately divergence. Now, if p is larger than 0, okay, in this case we define the function f of x is equal to 1 over x to the p. So we see this function satisfies our properties: positive, continuous, decreasing. Decreasing is the important property. So if we want to understand whether this integral is convergent or not, we have to, whether this series is convergent or not, we have to look at this integral here. Okay, but for this integral, we know already from last semester that it is convergent if p is larger than 1 and divergent if p is smaller or equal than 1. Okay, so this series is convergent if and only if p is larger than 1. Okay, this is something we memorize because this is an important class of series, and we will use this in order to compare it with other kinds of series. So you see that the harmonic series p is equal to 1 is the exponent which separates the good from the evil. Okay, so this is one example. There are plenty of other examples. So for instance, if you look at this example here, maybe just to get a rough feeling for convergent series, okay, it's always good to first apply your to have some heuristic argument which is good enough. Okay, so here in this case, you see that e to the minus n as n tends to infinity will go to 0 very, very quickly. Okay, so as n is getting large, this here will get small very, very quickly. So from this, you certainly expect that this series is convergent. Okay, so this will be your natural guess. Now, in order to prove this, this is pretty easy now because you just look at this function here, and this function is decreasing. Okay, so you can apply our integral test. So what you have to look at is this. Okay, this is by definition the limit t tends to infinity. So actually this symbol is a little bit similar to a series, okay? Because for a series we define a convergent series as the limit of the partial sums, and here for this symbol we define the convergence of such an improper integral as a limit from 1 to t e to the minus x dx. Is kind of similar because here you also add up the first over this range here, okay, and then you look at the limit, and if this limit exists here, then this symbol was called convergence. This is the same as this is a little bit similar, this kind of theory. Now, okay, so for this integral, indeed, it is easy to evaluate. Okay, and you see that it's equal to 1 as t tends to infinity. Which tells you, okay, this integral is convergent, hence this is convergent as well. Okay, so this was another example. Now let's look at one more example. So for instance, this one. Okay, so for instance, this one. So how about this series? Now, you see for this series, again, it's not so complicated because we can immediately apply the integral test. So what we are going to look at is this function here. Okay, so this function obviously is decreasing. Actually, this is enough for us. Okay, now, so what we have to look at is this integral here. Okay, and we all know how to handle such an integral. So, in order to discuss whether this integral is convergent or not, okay, we have to look at the limit as t tends to infinity, the integral from 1 to t dx over x to the cube plus x. Okay. Now this integral we can quite easily compute, okay, because it's just the integral over a rational function. So you know there is a kind of standard machinery how to handle such kind of integrals. So you see that because you can factorize the denominator as x times x squared plus 1. Okay, so what we are going to do is we use partial fractions. So we know this can be written as sum a over x plus sum b x plus c over x squared plus 1. Okay, and then we find a, b, and c. Then we plug everything in, and then we can integrate this guy here. And then we evaluate the limit. Okay, so you know everything is standard, so I don't have to do this for these examples. We have done enough of those examples last semester. I can tell you what the result is. The result will be convergent. Okay. Now, here, of course, I have dropped some details. Okay. So you have to do some computation here in order to figure out whether this is really correct. Okay. In particular, you have to go through the details here. Now, but I tell you what is more important, because we will actually learn easier tests which are more suitable for this kind of series. Okay. I will just let you know why just by looking at this series, it's already kind of clear that this series will be convergent. Okay. Namely, as n is getting larger and larger, okay, this n to the cube will be much larger than this one. So actually, you can forget about this one. Okay. But if you forget about this one, okay, then we have already seen that 1 over n to the p is convergent if p is larger than 1. So this will cause that this series is convergent as well. We will make this more precise. You see, this would be more complicated, okay, to carry this through. But what I said is not really precise, okay. But we will make this precise in the next section, okay. And we will see already for this series there's obviously an easier method to figure out that the series is convergent. You do not have to look at this integral here. This is not really complicated because it's standard. It just takes some time to figure out ABC, to integrate, but everything is standard, and then to compute the limit. Maybe let's do one more example, because I know from experience that students are not so fond normally of series and determining whether they are convergent or not. Maybe this is related to that it's not so easy to visualize series. So we should maybe look at some more examples. Now let's look at this one. So also this here depends on the parameter p. So it's a little bit similar to 1 over n to the p. The only difference is now that we have an ln of n in the numerator. But we will see that this doesn't make any big difference for the convergence behavior. Now, okay, so again, naturally, if you are faced with such a problem, okay, naturally the first thing you have to do is, as I said, you have to check whether this sequence here tends to 0 as n tends to infinity. For this, you see, as for the p series, that what you need is p is larger than 0. So if p is smaller or equal than 0, which will be your first case, if you look at the limit as n tends to infinity, ln n over n to the p will not be equal to 0. Okay, so from this already you know, okay, that you have divergence. Okay, now, so what is left is p is larger than 0. Okay, for p is larger than 0, you will define a function ln x over x to the p. Okay, and you notice, so what you have to check first is whether this function is really decreasing, at least starting from some large value x on. Okay, so what we do is, in order to figure out whether this function is decreasing or not, we will compute the derivative. So you see that this is 1 over x to the p plus 1 minus p ln x over x to the p plus 1. Okay, so this is equal to 1 over x to the p plus 1, and then you have 1 minus p ln of x. Okay, and you see that this is smaller than 0 if x is larger than e to the. Okay, so this is enough, because for some starting from some point, this function here will decrease, and from this property we know that okay, it's enough to look at the integral. Okay, so what we do is we look at this integral ln x over x to the p dx, instead of looking at this series. And normally it's easier for integrals, because for integrals we have much more tools in order to handle them. So you see that what we have to do is we have to look at the limit as t tends to infinity of the integral p ln of x to the p dx. Now, we have discussed integrals last semester, so integrals are trivial now for us. So in particular, this integral here is not complicated to compute. You see that the idea is integration by parts, because if you integrate ln of x, if you differentiate ln of x, it will become 1 over x, and you just have a rational function. So you will go one step in the you will do one step of the integration by part, and you will be able to compute this integral. For this, you have to exclude the case p is equal to 1. So now we have first again we have to split into cases. So the first case will be b is not equal to 1. Okay. Now for this case, you have the integral from 1 to t. Okay. So for this integral, we have ln x over x to the p dx. So we now use integration by part. So what you have is this is, so you integrate 1 over x to the p. So what you have is x to the minus p plus 1 over minus p plus 1. Here's the reason why we have to exclude this case here. Ln of x evaluated at 1 and t minus, and then you have the integral. So you have here, if we write here plus, then we have this here. And then we have x to the, so the derivative of this is 1 over x, so we have dx over x minus to the p. Okay, and this integral can be easily handled. So what we have here, if we plug in, so we see at the lower limit, because ln of 1 is equal to 0, so we just have to look at the upper limit. Ln of t, and what we have here is plus the integral. Okay, and this one is easy to compute, so now we have minus square. This is 1 t, and then we have x to the minus t plus 1 evaluated at 1 and t. Okay. Now, from this form, you see already that because what we want to do is we want to take the limit as t tends to infinity. You see that okay, so we have to look at this limit here. Okay, let's write this as limit t tends to infinity. Now let's first consider the part here was t. So for this part, we can in particular take out 1 over t to the p minus 1, and then the rest is ln of t over 1 minus p minus 1 over 1 minus p square. So this is this part here, and then we have left plus 1 over p minus 1 square. Now you see that okay, you have to look at two cases. If p is larger than 1, then this limit here will be equal to 0, because you have here this is just a constant, and here you have ln of t, and we know that if you have here some power, this power will be, as t tends to infinity, will tend faster to infinity as the ln of t. So if p is larger than 1, what we get here is that this limit exists, which means convergent for the original sum. And if p is larger than 1, and of course larger than 0, because we always look at this case here, then you see that this here will tend to infinity. Okay. In this case, what we then get is divergence. Okay. There's only one case left. P is equal to 1, but p is equal to 1 is a more simple situation, because in this case you have ln x over x, but 1 over x happens to be the inner derivative of ln of x, so you just use substitution. Okay, so for this case we already noticed that if p is larger than 1, we have convergence. If p is smaller than 1, we have divergence. Okay, so one case is left. P is equal to 1. Now for this case, we have to look at the integral from 1 to infinity ln of x over x dx. So again, this is the limit as t tends to infinity, and then the integral from 1 to t ln of x over x dx. Okay, and you know how to handle this integral, so what you do is you substitute u is equal to ln of x, because then your du becomes dx over x. Okay, so what you then have is the limit as t tends to infinity. Actually, also the upper or let's maybe okay. Also, the limits change, but let's maybe first compute. Let's first compute the improper integral, the indefinite integral. So what we have is the integral, and then we have just u du, and then at the limits 1 and t. So this is the limit t tends to infinity. Now we have u square half, but for u square we have ln of x. So we have ln of x square half, and now in the limit 1 and t. So what we have is the limit t tends to infinity, ln of t square half. This is clearly infinity. Okay, so also in this case, we have divergence. Okay, and now we know for all cases of p, for which p we have convergence, for which p we have divergence. So you see that the overall result is that if p is smaller or equal than 1, we have divergence, and we have convergence if p is larger than 1. Okay, so maybe let's summarize this. Okay, is convergent if and only if p is larger than 1. Okay, you have to observe that actually the same behavior for this one. Okay, for the p series we have the same behavior. Now, again, this is not a coincidence. Okay, because you can we know already from last semester that actually the ln of n, okay, compared to a power. Okay, so if you, for instance, if you compare ln of n to n square, okay, the ln of n is growing to infinity as n is getting large, is going to infinity much smaller than n square. Okay. Now, for the convergence of such a series, okay, what essentially is important is, okay, how does the series behave if n is getting very large? Okay, are the terms getting small fast enough? Okay, but the ln of n, okay, compared to the n to the p, you can almost forget it. Okay, you can think about it. It's like a constant. Okay, and if you look at this from this point of view, it's clear that the behavior of this series will be exactly the same as the behavior of this series. Okay, we will make this precise in the next section. Okay, and you will understand more clearly what I mean by this. Okay, but whenever you have given a series, okay, you should also first you should use some heuristic. You should you should look at the terms, and you should try to understand, okay, how fast are the terms growing to, how fast are the terms converging to 0 as n tends to infinity. And like this here, you can always compare it with other series like the p series and so on in order to get a feeling for the speed of this convergence. Now, so far, if we use the integral test, we can determine that such a series or such a series is convergent. Okay, if p is larger than 1. But as I stressed already at the beginning, and now another problem would be, okay, what is the value? So for instance, for p is equal to 2, what is the value? Okay, we saw already an estimate. Okay, so for instance, p is equal to 2. Okay, so for this case, we saw already that this series is convergent. But we also know more. Okay, we know this value must be smaller or equal than 1 plus the integral from 1 to infinity dx over x squared. Okay, so which is equal to 2. Okay, so we know already that the value here is smaller or equal than 2. Okay, but you should notice that the behavior of the convergence behavior of this series is the same as the convergence behavior of this integral, but the value is not necessarily the same, because the value here is 1. Okay, the value of this series, as I told you, is what was complicated to compute. Actually, this was a problem which was long open, and then finally solved by Euler when he was 17 years old. So Euler proved that the value is, from the answer you already see that it's not so easy. Pi squared over 6. I will prove this result maybe at the end of this lecture, so maybe in January, not in January, in June. There are many different ways to prove this. Euler certainly did it by using some elementary approach when he was 17, so maybe you have the tools already to prove this, because you are now older, right? You are not 17. But this is certainly, so do not try to spend too much time solving this, okay? It's certainly not an easy problem. As already mentioned, so we know already now for a couple of series by using the integral test that they are convergent, but we are still lacking tools in order to find the value. Of course, one of the tools we always can apply is approximation. So if you have, so this is called estimating sums. Okay, so if you have found that the series is convergent, okay, what you can always do is you use a calculator in order to compute S of n for some large n, and you will get an approximation or an estimate for the value of the convergent series. This is something you can always do. Now, in order to predict, okay, how good is, if you choose, for instance, n is, if you have given a series like an is equal to 1 over n squared, the one we saw before, and you choose n, for instance, 100, and you compute this here, you will get an approximation. But of course, in order to predict how good is your approximation, you need something to know about the error. Okay, so we need something to know about, okay, so if the value of the series, which we do not know, is equal to S, and we compute this as an approximation of S. Okay, what is the error? Okay, the error obviously is all the terms starting from n plus 1. Now, if you have used the integral test, okay, then you have already a function f of x which is decreasing, and an is equal to f of n. Okay, and again, you can use the following picture. And so on. So now our function, so this is our function f of x. Okay, so this is our function f of x, and you see that, so what we want to estimate is the error. So you see that if you interpret this sum here as the sum of the following areas of rectangles, so if you choose this here, okay. So you can interpret this sum here as the sum of the areas of these rectangles, and you see it here just from the picture that this will be smaller or equal than the integral from n to infinity f of x dx. Okay, so you can approximate this as the because you can approximate the area here of the white rectangles by the area below f of x and above the x-axis. So this is an upper bound. What we need as well is a lower bound. But for the lower bound, we look at a similar picture. Okay. We only draw the rectangles in the other direction. So again, let's say this is n here. This is n plus 1. This is n plus 2. This is n plus 3. And we go on like this. We have our function f of x. And now what we do is we plot or we draw the rectangles in the other direction, which of course gives us the same sum here. So also the area, the sum of the area of these rectangles is equal to r of n. But now we see, okay, we can, if we integrate f of x from n plus 1 to infinity, we get a lower bound. Okay, so we get that r of n must be larger or equal than the integral from n plus 1 to infinity f of x dx. Okay, so the error will be between the integral from n to infinity f of x dx and the integral from n plus 1 to infinity f of x dx. And this will give us an error estimate. And normally we can use this error estimate in order to predict, okay, if we really use this kind of rough approach to do approximations in order to predict, okay, how large is the error. You find some examples. Maybe I copy one of these examples from our textbook on the blackboard, such that just as you see how to apply this. So you see that we can bound the error from below and above by this integral. So for instance, if you look at this sum here, okay, 1 over n to the cube. So this one is convergent, as we know from the integral test. And now, for instance, if you compute S10, which is the sum of the first n terms, of the first 10 terms, then you get this approximation here. Okay, you should observe that this is a 9 here. You should observe that such an approximation is quite useless if you cannot say anything about the error involved. But we have here this error estimate, so we see that the error of the real value of this sum of this series to this approximation is smaller or equal than, and then just this integral here, so the integral from 10 to infinity dx over x to the cube, which is equal to 1 over 2 10 square, and this is equal to 0.005. Okay, so you see that from this you see already that a couple of digits will be correct. So this, normally the first two will be correct here. I just want to stress that actually you can use this in order to get a better approximation. Namely, you see that you can add the whole chain of inequalities with s of n. Then you get that s is larger or equal than this integral here plus s of n and this integral here plus s of n. And if you compute these two approximations, you will get something better normally for the sum s. You see also this example worked out here. But you see this, you can essentially use this here if you want to find an approximation of the value of this series, for instance, up to 5 decimal places. Then you can look here at the error, and you replace this 10 here by n, and you find n such that the error is small enough, and that's it. So numerically, we can solve this here. So numerically, we can find the sum of this series. But as I have told you, if you replace 3 by 2, okay, we know that Euler proved that the value is pi squared over 6. For this one, much more complicated, and no simple expression is known so far. So this is quite deep here. Okay, so any questions to this? Maybe an interesting example from our textbook is the following one. We know that using the integral test, we know that this series here is, also using the reasoning from last time, we know that this series is divergent. Okay, there is an interesting exercise in our textbook which asks you to discuss. So actually, we know that because this series is divergent, we know that if you look at this sequence here, this will tend to infinity as n tends to infinity. Okay. Now it would be interesting to know something about how fast does this tend to infinity as n tends to infinity. Now, if I say how fast, what do I mean? I mean does it tend to, if you look at this here, does it, as n is getting large, is this, does this tend to infinity as fast as like ln of n or n square or n to the n or n factorial? So we would like to know, okay, how fast does this tend to infinity as n tends to infinity? Now, the exercise which you have in our textbook is, okay, we consider this sequence here, okay, and the exercise asks you to discuss the properties of this sequence here. Now, the first thing you observe is the following. Actually, you can paint a picture. You can plot everything. Then maybe things are getting a little bit more clearer. So we plot the function f of x is equal to 1 over x. Okay, so let's plot this function. Now you see that. Okay, so this is 1. This is 2. We go on like this. So this is n minus 1, and this is n here. Okay, so you see that actually what you see here, the ln of n is the integral from 1 to t dx, 1 to n dx over x. Okay, so we know that, this was actually last semester definition of the limit, so of the ln. So where do we see this? So this is the area below this function here, from here to here. Okay. Now you see that, okay, but this here, as I have done already before, we can interpret this, okay, as we can interpret this as the sum of the rectangles, okay. So you see that the sum of the rectangles will certainly be, which is this here, will certainly be larger than the sum, than the area below the function f of x from 1 to n. Okay, so this certainly will be larger than 0. Okay, so you see here from the picture. Okay. Okay, so this is the first thing. Now, what we want to look at is the following. So we want to look at, actually we want to understand whether this sequence, so this sequence is bounded from below. Okay. We want to understand whether this sequence has any monotonic properties, so maybe monotonic, maybe decreasing or increasing. Okay, so that's why we look at Tn minus Tn plus 1. Okay, but if you practice in here, then you see this will be equal to ln n plus 1 minus ln n minus 1 over n plus 1. Okay, so the ln n plus 1 is from this here, the ln of n is from this guy here, and if you look at this sum here, here you have from 1 up to 1 over n, and here you have from 1 up to 1 over n plus 1. So most of them cancel out. Only this one will remain. Okay. So now the second part of the exercise in our textbook asks you to prove that this is larger than 0. Okay. Now again, you can use such a picture if you want to do this. So you see that. Because it's somehow related to the proof of the integral test. So you see that if we look at this here, okay, at this interval n from n to n plus 1, and if we look at the function f of x is equal to 1 over x, okay, then we can interpret this here as the integral dx over x, and we go from n to n plus 1. So this is this part here. Okay, minus 1 over n plus 1. Okay, so, and this part here is by the area interpretation, is the area below this function here. Okay. Now, this here you can also interpret as an area. Namely, if you plot this rectangle, okay, then this will be the area of the white rectangle. So you see that from this picture, you see that the yellow area will always be larger than the white area. So this will be larger than 0. Okay, so this was the first part of this exercise. You see this is in chapter 11.3, the last exercise. this was the first part, or the one of the last exercises. This was the first part to use such a picture in order to prove that Tn is bounded from below by 0. And the second part was to prove that this difference here is always larger than 0. Or in other words, this sequence here is decreasing. Okay, and now we know. So now we know that this sequence is decreasing and bounded from below. And this means by the monotonic sequence theorem, it will converge. Okay, so this sequence actually is convergent. You see, this sequence is pretty complicated. Okay, because it's defined as the first n terms of one of this series minus ln of n. Pretty complicated. Okay, but still we can use the monotonic sequence theorem in order to figure out that this series will converge. Okay, because we prove bounded from below. It's always the same idea. We prove bounded from below. We prove decreasing. Okay, and then we have immediately convergence. So Tn will converge. So this is convergent here. The question, of course, is what is the limit? Now, the limit is called gamma. This is another number which is famous in mathematics. This number is called Euler-Mascheroni constant. Okay, it's another famous constant in mathematics, like E is a famous constant, or pi is a famous constant. This is another one. Roughly speaking, this tells you that because this here tends to a limit, okay, so this tells you this is for n large pretty close to this one, okay. So because we know that this series is divergent, okay, so divergent means that the partial sums goes to infinity as n tends to infinity. But now we know also how fast, roughly like ln of n. You can compare it with ln of n. This number is, by the way, very interesting because we know almost nothing about this number. For instance, we do not know whether this number is irrational or not. Of course, we conjecture this number will be irrational. If you can prove this, you will be the first one, and you will get very, very famous. And you can write your name here behind it. Yes, already Gauss considered this problem, and Euler, and so on. So this is a very complicated problem. If you can prove this, then you are more intelligent than Gauss in some way. Okay, so this was one test in order to figure out whether a given series is convergent or not. Now, another very helpful test is the so-called the comparison test or comparison tests, because we will discuss more of them. Now, actually, this is already quite motivated to have such tests, because I told you already, okay, we already looked at this series here. Okay, we already looked at this series. We know we can apply, for this series, we can apply the integral test, because we look at the function f of x is equal to 1 over x to the cube plus x. This function is decreasing, and which means the convergence behavior of this series will be the same as the convergence of the integral dx over x to the cube plus x. And the integral dx over x to the cube plus x, we can handle it because we have tools for this. But I told you already, or we saw already, I didn't carry out the details, but this is not so easy approach. A more easier observation would be, as I already told you, so I want to stress this once more, that as n is getting large, okay, if you just look at the denominator, okay, then you see that n to the cube will be much larger than n, okay? So actually, it's kind of, as n is getting large, you can forget about this here, okay? So, and we know for such series, okay, 1 over n to the p, that they are convergent if p is larger than 1. So this kind of reasoning seems to be much more easier, and this should tell you as well that this series is convergent, but it's not very precise. So in order to make it precise, okay, so we first make precise, what does it mean, okay, that we can forget about this, okay. So actually what we have is, we certainly have this inequality here. So we certainly have that that the terms of this series are smaller or equal than 1 over n to the cube. Okay. Now, it's kind of what we would like to do is we would like to argue like this. It looks pretty good. Okay, it looks like it's okay. We can argue like this because this term is smaller or equal than this one. So the series will be smaller or equal than this series. This series is convergent, so this is convergent as well. Okay, this is almost correct, but not completely because we haven't proved something like this here for series. Okay, this for series holds as well here. In particular, you need convergence, and what we want to do is we want to figure out whether this series is convergent or not. Okay, so it's not completely true. Okay, now, but we can almost argue like this. Okay, instead of looking at the whole series, we look at the partial sums. So, okay, we look at the nth partial sum. Okay, now for this nth partial sum, we can certainly say, okay, this is equal to, this is smaller or equal than this one. Okay, because for sums this is true, and this is also because this series is increasing as n is getting larger, and will eventually, we know already, will approach its value. Okay, and this we know already that this is convergent. So what we see is that Sn, okay, is bounded from above, okay, for all n. So Sn is bounded for all n, and because Sn is a series, okay, where all the terms are positive, okay, so Sn is also increasing. Okay, and once more, we use monotonic sequence theorem. So by our monotonic sequence theorem, I told you that this result is an important result. So once more, we can use the monotonic sequence theorem in order to conclude that Sn converges to S, which then means that this series is convergent. Okay, so this is the way we argue. Now, but of course, you do not every time have to go into the details because we have a general result. And the result is as follows. But this essentially is the proof of the general result, which I just showed you. And this result is called comparison test, the first one. Okay, so what we need to assume is that that we have given two series and both of them, the terms are all positive. Okay, so two series with positive terms. This is important. Okay, the reason why this is important once more is because if you have positive terms here, the sequence of partial sums is increasing. And if a sequence is increasing, everything is getting much more easier because you just have to prove bounded, and that's enough for convergence. Now, so we have those two series with positive terms, and we have that an is smaller or equal than pn for all n equal than 1. Okay, and now what our result tells us is, okay, if you know that this series is convergent, then this series is convergent as well. And if you know that the sequence over the an is divergent, then the sequence over the bn is divergent as well. Okay, so this is of course it's kind of clear because if you look at this assumption here, an is smaller or equal than bn. Now you kind of this means you have for the series you can kind of think of as smaller or equal than here. So the series over an is smaller or equal than the series over bn. So if this guy exists, okay, this will exist, and if this guy does not exist, this guy will also not exist. Okay, so and this is a helpful tool in order to figure out whether a given series is convergent or not. Now, maybe I just want to stress that this assumption here, okay, it's enough if this holds for some large n. Okay, this is enough normally, because this is once more the same trivial reason, because you can, from every series, you can throw away a finite number of terms, and this will not affect the convergence behavior of the series. Now, let's maybe try to apply this to the series we have already discussed using the integral test, just to compare the two tests. So for this series, okay, we have already found by the integral test quite easily that this series is convergent. Okay. Now, how can you prove this using the comparison test? It's maybe interesting to check this out. Now, you just need one observation for this. Okay. If you look at e to the n, okay, we know that e to the n will grow as n grows to infinity, will grow to infinity much faster than any power. Okay. So, for instance, e to the n will be larger or equal than n squared if n is large enough. Okay. I don't really have to say how large. Okay. But we know that once more the reason is because e to the n as n tends to infinity grows faster than any power function. Okay. So the reason why I choose here n squared is more or less arbitrary. I can also choose n to the 3, n to the 5, or n to the 100. Okay. If I choose another power here, okay, this number maybe might get much larger, okay, because it takes some time till e to the n overtakes, okay, the power, okay. But we know that this is satisfied here, okay. And now from this here, you see that, okay, in other words, this means that e to the minus n is smaller or equal than 1 over n squared for all n is larger or equal than n0. Okay, so you have you can compare this series with the series 1 over n squared, but the series 1 over n squared is convergent. Okay, hence you can conclude that this series is convergent as well. Okay. Any questions? Any question? No or yes? No? Yes? You wonder about this here? Actually last semester, okay, we discussed the growth of this function here, e to the x, compared to the growth of a power function. This is a good question, actually, because maybe we should recall this. Okay, if you compare these two functions here alpha is larger than 0. Okay, now what we do is x tends to infinity. Okay, as x tends to infinity, we know that this function tends to infinity because like this. Okay, now. For this function, x to the alpha as x tends to infinity also tends to infinity. Okay? But we know that actually the growth of this function is much faster than this one. Okay? Now, what does this mean? What do I mean by the growth of this function is much larger than this one? Now, precisely speaking, I mean that if I compare those two, okay, like this here, then no matter how large your alpha is, no matter how large you choose this, you can choose it 1,000, 10,000, okay? This limit will always be infinity because this function grows much faster than this one, okay? But from the limit definition, okay, this already means that, okay, if you look at this function e to the n and the function n squared and you plot the function e to the x and x squared, you will see that starting from some large x, okay, this function will be larger than this one, always, okay? So you have kind of, this is not necessarily true for, this maybe is, for 2, maybe it's true for all n, but this is not, if I replace here 2, maybe you can try to prove that it's true for all n, but it's not essential. Essential is it is true for some large n, from some large n on, okay? if I replace here 2 by something different, like 100, this will also be true. But maybe this will change here. Okay. Now, so this means that this function is always smaller or equal than 1 over n squared if n is large enough. Okay, and this will be enough. Here you see actually, of course, here I write for all n larger than 1, larger or equal than 1. But this can be replaced. The 1 here can be replaced by any large number. Okay, but because this essentially boils down to throwing away terms here from the series, which does not affect the convergence behavior. This explains your question? This answers your question? Okay. This is something important to understand, okay? The important thing which I want to stress here is that you get a feeling for why this series is convergent. Not just, okay, you can apply the test and you see, okay, the series is convergent. The important thing is, why is this series convergent? The reason behind this, the reason behind the fact that this series is convergent is that e to the minus n tends to 0 very, very quickly as n tends to infinity. Which means that because you add here terms, now if this goes to 0 quick enough, okay, then the terms you add are getting smaller and smaller, and you will finally reach some number, okay. But if this does not tend to 0 fast enough, okay, then what you add is maybe always too large, okay, which will cause that the partial sums are growing. Okay, this you want to avoid if you want that the series is convergent. Okay, so this is one example. One more example. One more example is this one. Okay, so we already discussed the behavior of this series. So for instance, we know that if, for instance, if p is larger than 0 and smaller or equal than 1, then we know this series is divergent. Okay, so for this range, okay, you see that ln n over n to the p, okay, because the ln n is something like if n is large enough, not necessarily 1, because 1 this guy is 0, okay, but starting from 2, okay, you will see that this is smaller or equal than 1 over n to the p. Okay. Now you see. Now we know that this series is for this range of parameters is divergent. Okay. So you use a comparison test and you know this series. So the original one, call it star. So star is divergent as well. Okay, so it's much easier like here, because when I use the integral test, I have to compute this integral, I have to use integration by part and so on. It's not really complicated, but too much details, okay? You have to do too much computations, okay? Life is much easier if you use the comparison test. Now, but how about the remaining range? So if p is larger than 1, okay, how about this range? Now, what you have to find is you have to compare this series with another one. And from the other one, you should know already that it's convergent. Okay. Now, which one do you choose? Now, again, I said that e to the n, okay, is growing, as n tends to infinity, is growing faster than any power function. But you know that the ln of n, okay, is growing to infinity slower than any power function. Okay. So, for instance, if you fix any epsilon small, okay, so epsilon is like as small as you wish, but of course larger than 0. So for instance, epsilon is for instance you choose 0.001 or something like this, okay, because this function, okay, is growing slower to infinity as any power function. You certainly have this here for all n large enough. Okay, but this means that ln n over n to the p, okay, it will be smaller or equal than n to the epsilon n to the p. Okay, and this you can write as 1 over n to the p minus epsilon. Now, if you choose, because your p is larger than 1, okay, So if you choose your epsilon small enough, this here, p minus epsilon, will be larger than 1 as well. Okay, you just subtract a little bit. Okay, but then you know that this series here, the series over those guys is convergent. So the series over those guys will be convergent as well by the comparison test. Okay, and you see this is much easier than using the integral test. And essentially this is what I told you before when I said, okay, you can kind of neglect the ln of n. Because the ln of n compared to this function, okay, the growth of this is very, very slow. Okay, it's almost like a constant compared to this. Okay, and this is kind of making this precise. Okay, so you see that the essential thing which you do not find in our textbook and which I want to tell you is that if you want to figure out whether such a series is convergent or not, okay, you have to in some way you have to understand, okay, how fast does the term tends to 0 as n tends to infinity. Okay, if the convergence to 0 is fast enough, you normally have convergence of the series, and if the convergence is not fast enough, then convergence will fail. Okay, so any questions? If not, you will find the first assignment online today after the class. Maybe you have to wait 1 or 2 hours. Then you can download it. And you have to handle in the first assignment next week on Thursday. Not next week on Monday, next week on Thursday. The reason why I put it online today should be clear to you, because on Thursday, unfortunately, we do not have class. Okay, if there are no questions, then that's it.